what I will show is the constraint satisfaction solver. And what we found is that it is actually fast and efficient compared to CPUs. So these constraint satisfaction problems are a very generic and applicable kind of type of problems. However, they are NP complete. This means that they are intractable, although decidable. So conventional architectures still have challenges to solve that. So scalability, for example, is a challenge for certain algorithms. Then you rely on heuristics to be able to overcome these scalability issues sometimes, like using local search. And then you need to do trade-offs, like, for example, if you are solving through algorithms like backtracking, then you are guaranteed to find a solution if it exists, or all the solutions if they exist, but then you have poor scalability. So you have different issues in classical architectures because of the nature of the problems that are intractable, right? And then we take the advantages of the stochastic spiky neural networks. And some of these advantages, or most of them, are very familiar to you. So one of them is sparsity. So when we take, for example, this square here is showing the connectivity matrix of a constraint satisfaction problem, where the purple background is zeros and the yellow very small squares are ones, right? So there are connections in the yellow squares. And you see that most of the matrix is actually void, it's actually without connection. So this kind of sparsity is actually very nice for spiky neural networks, because then you will not have a lot of traffic, and the constraint satisfaction problems are sparse by nature, and they use local information. So these are features that are shaded with spiky neural networks and are very interesting. And also when you put the stochasticity on a spiky neural networks, we know that you can encode probability distributions, and you can then start to make some probability distributions operations with spiky neural networks, right? And you also have dynamic properties like chaos and these kind of dynamics that are very special and allow you to explore state spaces quite efficiently, right? And we also have this precise timing, that is this new variable that we put into the spiky neural networks. And actually this timing gives you some precision and avoids that you need to finish certain processes if you're able to capture the important information on a precise time. And because we can map directly these problems into spiky neural networks, then the growth of the spiky neural network actually is proportional to the growth of the constraint satisfaction problem. And then to harness these advantages of spiky neural networks, we can use neuromorphic hardware, right? Because it's kind of especially built for that. And neuromorphic hardware brings fine parallelism, right? So you have all of these operations in the search space happening at the same time, and you have the event-driven characteristic of, in this case, Loihi, but most neuromorphic hardwares, where you are actually hiding this precise timing that we have as an algorithmic advantage on spiky neural networks. And then finally, we have this compute and memory integrated, so that you don't really need to transfer too much data for communication. So this is just kind of overall motivation of why using neuromorphic hardware for these kind of problems, that maybe they are not as brain inspired as deep neural networks, but there are a lot of advantages of implementing this in neuromorphic hardware. So now that we have a good motivation, let's go to the formal kind of properties of what is a constraint satisfaction problem. So the definition itself is just you have a set of variables. All these variables can take on, each one can have its own domain, be it a numerical or you can put any kind of values that you want to take on these variables. It can be colors or whatever. And then you have restrictions over the domain, over the values that these sets of variables can take on, right? Then you take subsets of these variables and you put some restrictions. And you can see that this is actually very generic, and you can put a lot of real world problems in this formulation. And once you have this formulation, the actual problem consists in finding assignments to the set of variables so that all these relations are satisfied. So if you can encode your knowledge of the world into the relations between certain sets of variables, then you have a constraint satisfaction problem. And the problem is that these variables will create an exponentially growing state space. And then searching for solutions becomes very hard, right? And but the advantage is that you can check for solutions if you have them very efficiently, right? So this makes the problem very interesting. And to tackle this kind of problems, then the first thing that you will do is for low heat, we formulate it as an optimization problem. So we unroll these variables into a one-hot encoded vector, so that it's easier to map to the spiky neural network. And we encode the restrictions of being a one-hot encoded vector and the constraints, so these relations are, we encode them in an adjacency matrix between these one-hot encoded vectors. And each one of the elements of these vectors will be a neuron, right? So in this sense, this energy function is actually counting the number of relations or constraints that are satisfied or not. If all the relations are satisfied, then this energy will be zero. So the problem of finding the assignments to X that satisfy the constraints has been transformed in an optimization problem on a binary variables domain. And then I can go ahead and map this to spiky neural networks. So each variable will be a winner-take-all circuit made of neurons that are interconnected between them, and then most of the time one of them will fire, as you know, and then we can start to code the constraints between these variables. In this case, we have two variables that have the constraint that they need to have different values. So we use a one-to-one inhibition between these two winner-take-all motifs to create these constraints. So if our constraints are that both variables should have the same values, then I need to either make these connections excitatory or shuffle this around so that you inhibit the complementary domain of the other variable. The point is that you can use these synaptic resources to map constraints, and you can use the neurons to map variables and their domains. And what becomes more interesting is that if you put noise on in these spiky neural networks, actually as shown by Jung, and from the group of work on maths in 2 grads, these stochastic spiky neural networks actually sample from a probability distribution which favors low energy states. This formulation, both in terms of probability distributions in this Boltzmann-like shape, and this encoding comes actually from the 80s, from the time of Hopfield, when he was working on all these artificial neural network problems. But then, and this gave rise to the Boltzmann machines that then gave rise to simulated annealing. But then now we are seeing that going a little bit in that direction is actually bringing advantages to neuromorphic hardware. So the point is that these neurons will then start to sample from a probability distribution that favors low energy states. So if one of these energy states has actually energy zero, that means that I have found a solution to my constraint satisfaction problem. And interestingly, because these are neurons that actually kind of have these dynamics in time, in which they accumulate input, then they spike. And once they spike, they are mandatorily, they are demanded to come out of the refractory period with certainty. That creates an asymmetry between the probability of firing and of coming out of this firing state. And that forces these winner-take-all circuits to take a kind of undefined states in which either several domains are active at the same time or none of them. And if I see here the energy landscape of this kind of this problem in this case, I can actually jump high energy barriers that are difficult to get kind of states, because I prefer low energy states. But then because I can acquire with spiky neurons, I can acquire these undefined states. I can bypass these energy barriers, and then that allows to solve the problems quite efficiently, right? So the way it goes is, if every one of these rectangles is my spiky neural network, then certain neurons will fire first because of the stochasticity, and then this will inhibit the neurons to which it is connected, and then the state will start to get pruned to satisfy more and more variables, or find a better configuration. And this will go forward and backward until at some point you get this very favorable configuration that encodes the solution to these problems. So this is very nice, but previous approaches, including mine with Spinnaker, were kind of recording the state of all these neurons and checking at every time step or after in a post-processing phase, searching through all these network states that is kind of quite massive if the network solved the problem. And this is actually not quite efficient because you are demanding a lot of either memory or traffic of information. So the approach to make this really kind of competitive as a computing solution is to actually avoid this probing part of detecting kind of the state of every neuron at every time step. So for the implementation in Lowihi, we take the challenge of detecting the solutions online and only extracting from the chip the solution once you have it, right? So the way we solve this is we realize that the energy function that I showed you above, actually this part in here is already computed by the neurons themselves. So if you see, this is kind of the synaptic weights, and this is the state, the spiking state of the presynaptic neurons. And these are actually the current components. If we see the neural dynamics of our Lowihi neurons, the current is actually getting this information already. So that means that if I multiply this compartment current by the spiking state of my neuron, I actually have a component of the energy function that is kind of a local energy of my network. And then I just need to sum over all these local contributions, and then I can online detect with a summation neuron that will perform the summation, integrating spikes of this type that comes from all the neurons in the network. Then I can detect when this summation reached a certain value, in this case, 0, or, well, I can put a threshold that signifies that the energy is 0, and that means that I can detect solutions online. So I can leave my network, make the search, and once the network notifies me that the energy is 0, because this summation neuron spikes, then I can decode the state of the network, right? So just to show here in the voltage, we are including this random perturbation to create the stochastic behavior of the neurons. So that means that we don't need other population stimulating with Poisson spikes or something. The actual variable is already random. And we realize also that because of this that I just explained, the current of the compartment is actually performing stochastic gradient descent on the energy function, right? Or something like that. Then other important component here is that we are using box synapses, and this allow that the binary variables are actually well defined during this length of the box synapse, right? And this allows to certain states of different neurons to converge in time to the solution, and then produce kind of the value of this summation. So here in this part, I am showing you more or less kind of a very big picture of how we implement this in Lowihi. So we use multi-compartment operations. And then these two blue circles represent a compartment, for example, that is actually performing the integrate and fire dynamics. And on top of this base compartment, I create other compartments that actually make this computation of zeta I, of the local contribution to the energy function. And then they send spikes to another neuron in my network. That is the neuron that will integrate actually the value of the energy. And then now at this point, I only need to use the on-chip x86 processors to monitor one neuron instead of the perhaps thousands or millions of neurons that I will have in my network. So I only monitor this neuron. Once this neuron has spiked, then I know that I need to stop the simulation or the hardware and go and retrieve the state of the neurons, and that will encode the solution to my problem. And what this brings is that we have not expensive probing of the states of the full network, and this allows a very fast evaluation of the cost function, and then the solver itself is becoming competitive. So just to show you how this actually work, I need to just one sec. I cannot see I think, okay. So in Lowihi itself, I am showing you here how we create the standard Sudoku problem. We encode it in different winner-take-all neurons groups, and then we allow them to search for different configurations. And you see in the cost function here below that it gets some kind of stuck in some local minimum, but it tries to get out. It tries to get out like it is reasoning. Oh, sorry about that. Can go ahead again. Like here. So what I wanted to show you is just that because of this nature of the spiky neurons, that they can have these high energy states mandatorily, you see here how the energy barrier has been jumped. And then you get out of local minima and you get to the solution of the problem. And the network just gives me that solution, right? And just another standard problem, that is the map coloring problem of the world. This, I have put 5 colors so that it is way faster. And if the problem is trivial, then the network will very quickly converge to a solution, right? So now we go to the more interesting part, that is benchmarking this, measuring the energy and the time that you need to solve this problem, and comparing this against the state-of-the-art solutions. Because what we want to know is, are these problems interesting enough so that somebody will change their state-of-the-art approach by a neuromorphic technology? Then as we are handling here NP-complete problems, we can pick an NP-complete problem and benchmark it, and we can draw some conclusions over different kind of problems, because you can map in polynomial time any NP-complete problem to any other NP-complete problem, find the solution, and transform back. So we pick this Latin squares problem because it is familiar, easy to understand, and also you can scale it 1 by 1 size, right? So the Latin square problem consists in this array of cells in which you will have the restrictions that in a column or in a row, you can only have one occurrence of every of the digits. So if you have a 9 by 9 square, like in Sudoku, you can only have a digit occurring once per row and once per column. And then you can scale that up. And for encoding this in the spiky neural network is exactly what I showed you. And we use winner-take-all neurons, winner-take-all motifs. And in this case, it will have 9 neurons, and they will be connected so that most of the time, one of them spikes. So they acquire random valuations. And then I create connectivities encoding the constraints between all these winner-take-all circuits. And that gives me the network that represents my problem. And then we took a state-of-the-art solver, open access in this case, that is CBC. CBC is a CoinOr. This is an organization that produces several solvers for operations research, kind of this optimization kind of problems that are very used in planning and scheduling and these kind of problems. And then they use linear programming, and in particular the branch and code strategy, to find solutions. So we are not benchmarking here against, I don't know, Nest running on CPU. We are benchmarking here against a standard state-of-the-art solution like linear programming, solving the same problems. We do take a solver that is incomplete because our solver is incomplete. So we may not find the solutions or all solutions. We are not guaranteed to have that. So we need to make an apples to apples comparison. And in that sense, we pick a state-of-the-art solver, but at the same time is an incomplete solver. And the results of this incomplete solver, scaling Latin squares, are the red lines here, and low will be the blue lines, right? And what we do is we take the 2 by 2 Latin squares problem and scale it until 20 by 20, right? And then as you grow in size, then you require more neurons, more cores, more synaptic resources as well. And the difficulty of the problem increases. So you will notice that these are logarithmic scale plots, and this linear behavior actually means that the solvers are taking exponentially more time in this case to solve the problem, or exponentially more energy, right? And the interesting result here is that if you see low E lines are below the CPU lines. So this means that in energy, we have between 3 to 5 orders of magnitude better energy in low E, which is quite expected. But we also get an order of magnitude enhancement against CPU on time to solution. And this altogether gives us like 3 to 5 orders of magnitude in energy delayed product, right? And we also see, for example, this is interesting. We need to expand more, but we see that the tendency of low heat is actually a little bit better, like sub-exponentially apparently, a little bit compared to the standard solution, right? And here in low, we are decomposing this time to solution component of low heat in the two components, the time per time step, so how much real time takes low heat for each one of it, the steps or iterations of updating all the neurons of the network, and the number of steps that you take to solve the problem. And then we see that actually the step time per step, it actually grows in the beginning because we are updating the neurons sequentially inside a core, but as you go beyond one core, still below one chip, all this is in a single chip, in a single low-end chip, then you just get to more or less constant value of your time per step, but the number of steps that you require to solve the problem grows exponentially as is expected for these kind of problems, right? Because the state space is growing exponentially. But overall, we are seeing nice advantages, and we have had a paper accepted showing this and other very interesting low results on the IEEE proceedings. So you can check that soon. It's not in the review anymore, it's accepted, and will be published in one of the next issues of the IEEE proceedings. So interesting issues here are, I will just show you a phenomenology that we observed that shows that there's still a lot of research to do in this area. So if you see, here is more or less the same plots as in the previous slide, but then the light blue line has a less correlation and between the random numbers exciting each one of the neurons, and the dark line has more correlation, right? And then we see that the correlation of the random numbers in the network actually improves the time to solution for almost an order of magnitude. And this surprised us because first, you will expect that uncorrelated noise will actually create a better time to solution. But we observe the opposite, and it's actually a good advantage that we are getting here from only increasing the correlation in noise. We arise to this conclusion or to this phenomena because the way in low heat we apply noise is to randomize the voltage of each of the neurons. We apply these LFSR numbers that comes from these random pseudo-random number generators, and a single LFSR fits a whole neurocore, right? And then changing the grouping between the number of neurons that go in a neurocore, you can actually change the number of neurons that are affected by a single LFSR. And then you get this way of varying the correlation between random numbers. This is not really relevant. The important thing here is that we see that the noise correlation is actually affecting time to solution, and we need to do more analytical research to understand how to improve even further this solver. So we have some analytical results and that show that actually the variability on the energy function is improving as you improve the noise correlation, but we are in the process of understanding this at a deeper level. So the second task that I want to show you that we benchmarked in low heat is train scheduling. So we have this cooperation with Deutsche Bahn, the German operator of the train network. And the problem for them that we are trying to solve, or we are solving with low heat, is that you have this network of nodes, and each one of these nodes is a train in a track in a particular time, right? And this will represent kind of the rail network in Germany, but including all the vehicles and time constraints, right? And then for in this network, you get certain requests, and the request will mean I need a train at a particular time in a particular station, and I need that this train goes to another station and arrives at a particular time using possibly this or this other track, right? So the problem for them is that they get these requests, And then they need to find the paths to put these trains in motion, but you cannot have conflicting, you cannot have two trains on the same track at the same time, of course. So what this creates is a constraint satisfaction problem in which you have these requests and you need to make allocations of roads so that there are not spatial-temporal conflicts between them and they can kind of move freely. So this problem is actually mapped into a binary constraint problem with a couple of constraints, and they use a commercial solver that's even better than CBC and to solve this problem. And then we benchmark this problem solving it in Lowihi. How we solve it in Lowihi? So we have these winner-take-all motifs again, and each one of the values in these winner-take-all motifs represent one of the candidate roads that I have. And then the constraints between the roads, the different routes that you can take on with these trains at these particular times. Then you have certain constraints over them, and then you use again synaptic connectivity to map these constraints into your spiking neural network. And then we use the same strategy of online validation and detecting a solution to map this problem. So the scaling in this case is a bit different from the Latin squares problem scaling, because as you scale the problem, you are actually increasing the number of candidates that you have. So you have a fixed number of requests, that is what you are asked to provide. And then you getting these candidates is quite expensive. So you don't want to get kind of a very large number of candidate roads for this problem. So you start very small and then you start to grow, trying to reach more satisfaction on the number of requests. So in this plot, the red line is the number of requests that you are asked to. And the yellow line is what this commercial solver can achieve, right? And the blue line is Lowihi. And as you grow from the left to the right, what you are doing is getting more possible routes to solve this problem. And then what this means is you need more neurons, cores, and synapses in Lowihi, but the problem gets actually also more tractable, at least in theory, right? And it's interesting because if we see to the time plot here, actually for the commercial solver, even that the problem is getting easier, the commercial solver is needing more and more time, right? And also more and more energy to solve the problem. Well, Lowihi actually shows you that it doesn't require more time. It actually starts requiring certain time, and then it starts to slow down to require less and less time, so speed up. And then when we look, why is this happening? We see that here making the decomposition again between steps to solution and time per step, we see that in the time complexity of Lowihi is actually flat. And this small decrease in, so the bad time at the beginning is because we have a lot of spike congestion at the very start in the problem where we only have one candidate per request. But the thing is that the spiking neural network solution can actually have this flat complexity in time for solving this kind of scaling of problems, which is actually different of what the conventional solution finds. And we still are between 90 and 98% of accuracy or satisfiability actually for these problems. But we are getting kind of, again, certain advantages in time for the largest problem and in energy. And that means that in energy delay problem, we can get between 3 and 4 orders of magnitude better performance than a commercial state-of-the-art solver. So this is what we mean, that we are going in the direction of becoming competitive for real world applications against state-of-the-art solvers, right? So this is more or less the end of the talk. I will do a small tutorial after the conclusions to show you how this runs in the actual platform, right? So overall, we see that we have both speed up, so we have orders of magnitude, or better time and better energy. So overall, better energy delay product, right? And this is like 1,000, 100,000 better kind of performance than state-of-the-art applications, right? And the fact that we can even show advantages in a commercial solver is actually quite encouraging. This comes from the fact that we have a sparse activity due to the winner-take-all competition, and well, all the features of the spiking neural networks and of the neuromorphic hardware that I showed you at the beginning Plus the fact that as we are not probing neurons, we are not probing the state of the neurons, but we are having this on-chip validation strategy, actually saves a lot of energy, memory, and data traffic, right? So we are in the process of scaling this up further. So for this problem in here that I just showed you, we are going actually now, we are in the 25,000 binary variable size, for which we are still using two low-E chips. But we are in this process of scaling even further, and we have kind of the aim of having a dynamic hyperparameter kind of optimization, so that you don't need to make this hand tuning that is conventional in a spiky neural network. So we want the network to adapt to the search processor. And in the next generation of the chip, we will actually have increased efficiency, more flexibility to actually tackle another kind of either CSP problems or other kind of optimization problems. So that will be coming in the future. So also stay tuned for that. And then I will just show you very briefly. So I just want to share with you a little bit of how is the feeling with the platform, because the other problem that we want to kind of solve with Lowy here and with the Lava framework that Andrea showed is that we want these solutions to actually be kind of easy to use, right? Like when you import a library in Python and then you solve your problems and you don't need to care about the chip and all the configurations as we heard in some of the talks today, right? So this is a Jupyter tutorial. I already explained you all the constraint satisfaction formulation and encoding in spiky neural networks. But then just a little bit of detail on the solver itself. You have the spiky neural network. You have this reporter neuron that integrates the information, and then it sends to the x86 processors the information that you have solved the problem. Then this says to the host, hey, go detect the solution that we just found. And then the host should request the network to provide the solution, and then it provides to the host. And this is interesting because then you can go ahead and say, okay, I want another solution, or I have new constraints, so I can use another SNP and modify the network if I want and continue the search. So this actually opens avenues for several interesting things like dynamic constraint satisfaction problems or things like that. And then the solver itself, well, we know already that we need neurons, the synapses, and the synapses encode both the winner calls and the constraints of the problem. And we have the energy formulation where we will look in the next cells how we are monitoring the summation neuron. Actually, the spikes of the summation neuron can be used to actually know how the solver is actually performing without needing to look at all the neurons of the network. But we can do that. So in a sense, what you need to do is, for example, here, import your solver, right? Or import a sub-app of the solver. For example, you can import the constraint satisfaction solver or you inherit from it and create your own class, and you create a Latin square solver, right? So then just to show a minimal example that is easy to visualize, if you consider the map of the territories of Australia and the map coloring problem of assigning 3 colors to these territories so that not bordering territories have the same color, then we can just create a dictionary with the one node for each one of the territories. You just put the constraints of what territories are neighboring with each other, and then you just create the CSP solver and solve. So if we are lucky, this will, no, not lucky. I mean, this is actually the Jupyter notebook talking with the Lowy or with the host to ask it to search a solution for this problem. So one of the parts that we are still working on is in speeding up this process of actually compiling, but then the network itself found a solution at this time step 45 and reported the solution. And this is the write that I got from the spiky neural network. No probing so far. Still, I can kind of just visualize what the network found. And then if I see there are not adjacent nodes in this network that have the same color, right? So this is just a trivial example, but it shows how you can actually use the solver without referring to all the overhead of even what is Lowy. So the idea is that Lowy is just another backend that you can use for solving that problems. So for the Latin Squares app, you can do exactly the same thing. So you just specify the size that you want, and then you let the stack, the computing stack to take over. So this just takes a bit of time. And well, this took a little bit longer, but then it finds the solution, the network decodes the solution and gives you the result to it. And if you want to visualize a little bit nicer, you can do so. But then we can also cancel a bit of the process, but just probe the summation neuron. So I am just canceling here the snips that configure the part of the online validator so that I can show the full dynamics of the network. So if I run the network, probing the summation neuron, I will see actually the number of satisfied variables that my network has had through time, right? So I am here putting a red line where the maximum of satisfiability is. So I am here plotting, it's just the current of the summation neuron, but then it shows the whole progress of the stochastic search where it finds a solution, and then it is in this stable probability distribution of states in which it visits the solution very often, right? And sometimes you can get different solutions here, right? Depending on how you configure your network. And what is interesting is that as this is a threshold on the summation neuron, I can actually modify it. So I will say, okay, I want now to find just 80% of satisfiability because I want something that is very fast, and I am happy with 80% of satisfiability. So I just need to lower the threshold of the summation neuron, and I will actually execute this one as well. Yes, the fact here is that I can get a solution that is partial, right? I'm lowering the threshold of satisfiability that I am asking the solver, and then I am asking, hey, find me this solution, and then as you remember, it was like 10,000 steps in the previous run. Here is 61 because it's just 80% of the satisfiability that I am asking the network to give me. So it is way faster, right? And then if we see here the solution, the gray winner take-alls here are winner take-alls that are violating the constraints. But I was only caring about 80% of satisfiability. So I will make use of the ones that are satisfying my states, for say so. So that's something interesting, perhaps when you are in a real world environment and you need this very fast response, right? Still, if you want to explore the whole network and every spike that is happening there, of course, you can just use the, oh, what happened here? Okay, somebody closed my connection. You can, of course, just call, okay, I want to see what the network is doing. Okay, just one second, just network issues. The point is, well, I have actually pre-run this so I can show you the results here below. So you can see for this partially solving a network, you can see the raster plot of each one of the neurons, and you can see an offline evaluation of the cost function or energy function and the different variables that your network neurons actually have. So if you want to do this inspection, of course, you can do it. But the interesting point is that you get a very user-friendly solution. So just to kind of close it up, I just want to run the solver for different sizes of the problem to something that is showable in a very short time. So let me see if this cell here is still executing. Well, and this time is not that normal, it's usually faster. So apologize for that. I will actually stop this one. And this one is actually slower because it is recording all these states, which is actually very interesting because it is showing kind of the overhead that you pay when you record the states of the network, right? Besides the memory that you are spending for that, right? So now we try to run the scaling. It works, I promise. Oh. Yes. Go ahead. Sorry. Okay, so it starts to actually find the solution to different Latin squares problems from 2 to 10. I actually put it here, but then this takes like 1.5 minutes to show the different solutions and the time it finds every one of these solutions. So this is a scaling up of the problem. Yeah, so sorry, I'm having some socket closing of the connection, but then I see the different solutions that were found by the solver here and below, and you can see that you're satisfying the different constraints of your Latin square solver. So I will just go ahead to questions if there are any, but this concludes kind of the presentation of the constraint satisfaction solver. And if there are no questions, we can go to the next presentation.